Good morning, children. This is lecture 4 of the chapter Chemical Kinetics. In this lecture, we will do collision theory and transition state. The last lessons that we have covered: rate of reaction, factors affecting the rate of a reaction, law of mass action, rate law, rate constant, order of a reaction, zero and first order reaction, half-life of a reaction, experimental determination of rate law, rate constant and order of reaction, integrated rate law, and some numericals based on order of reaction. Collision theory of reaction rate. You all know that for a reaction to occur, the reactant molecule must collide with each other. Without the collision of the reactant molecules, a reaction cannot take place. Now let us see what is written here. The first point is given: a reaction occurs when reactant molecule come close enough and undergo a collision. As I told you, without the collision, the reaction cannot take place. Number 2, all collisions do not lead to a product. That means the reactant molecules are colliding with each other, but all the collisions will not lead to a product. Only a fraction of total number of collisions are effective. Now, which collisions are effective? I'm saying that all the collisions are not effective. So, which collisions are effective? Only those collisions lead to a product where reacting molecules acquire a certain amount of energy. That means for getting a product for a particular reaction, there is a certain energy requirement. The reactant molecule must collide with each other with a certain amount of energy. And then only the reaction will take place and we will get the product. Factors affecting effective collisions. What are the factors that is giving effective collisions? There are two factors. One is energy factor, another is the orientation factor. So it is termed as energy barrier and orientation barrier. What is this energy barrier? Energy barrier is saying only those collisions having at least a definite amount of energy or more, they will result into useful reaction and leading to a product. That means what? When a reaction is taking place, the reactant molecules, they are having the kinetic energy. With that kinetic energy, they are colliding with each other. Now, after the collision of the reactants, if it is crossing a certain energy, that energy is particular for a particular reaction. Okay, when the reactants after collision, that collision is crossing that energy barrier, then they will go to the product side. And this energy is known as threshold energy. This is a new term and this is a very important term, threshold energy. Now come here, see this graph. Now this graph is showing you the kinetic energy of the molecules, that is the reactants, and the fraction of molecules in y-axis. Now you see, if you can plot a graph, now this is the energy barrier, that is the threshold energy, this one. Okay, now these fraction of molecules, which is shown by the blue color, these fraction of molecules, they cross this energy barrier, that is the threshold energy, and these collisions, when after the collision they will cross this energy barrier, they will lead to product. And This will increase with the increase in temperature. As you will increase the temperature, the kinetic energy of the reactants will increase. So more collision will take place, and because of the collisions, they will get an energy. And if that energy is crossing that particular energy, that is the threshold energy, then they will give you the product. This is one, energy barrier. Another is orientation barrier. Now, orientation barrier means the collisions, when the collisions will take place, these collisions, for getting that collision, the reactants must collide with a proper orientation. So what is written? Those collisions in which the reactants are oriented in a favorable direction. Okay, so just see here in this figure, see this is the reactant A and this is another reactant B. Now A, these are the reactants, and B, these are the reactants. Now these are placed in this way, so this is a proper orientation. This is a proper orientation. Now after collision, they are giving you this type of collision is taking place. So these are the effective collisions. Okay, now this is giving you the product AB and AB. This is a proper orientation. Now come here, this is an improper orientation. AA in one side, this side like that horizontally, BB is another side. So this is difficult for them to collide with each other and form the product. So this is the inactive collisions and no reaction will take place. Am I clear? Now in this slide it is showing that all collisions do not lead to product. This required a proper orientation. Now there are 4 types of collisions shown. We are having 2 molecules. This is one molecule and this is another molecule. This is in case 1, what is happening? The second molecule is coming and attacking the first molecule. The first molecule is having a double bond. When the second molecule is coming and attacking the double bond should break. So this is the first case is the proper orientation. If this is the case, then it can open the bond, double bond, and the reaction can take place. Come to collision 2. Now if this is the arrangement, now this green part is coming, that means it is the size is bigger, so it will not fit here. So this type of collision is not effective. Come to the third one. See the third one. It is attacking from this side. Now this side also, it is not a proper collision. The product will not form. Come to the fourth one. The fourth type, it is attacking from this side. This is also not the proper orientation and the product will not form. So that means all collision do not lead to product. For that it is required a proper orientation. Collision and reaction rate. The reaction rate in principle depends on the speed of the reactants that collide with each other. The reaction rate is fast. Fast reaction rate means the particles are moving fast. Fast moving particles. If the particles are moving fast, the reaction rate is fast. Slow reaction rate is equal to slow moving particles. That means particles are moving slowly, so reaction rate is slow. There are other factors as well on which the rate of reaction depends. Now let us see on which factors the reaction rate is depending upon. This already you have seen once. Then also once again, the rate of a reaction is depending upon the chemical nature, temperature, if the catalyst is present, concentration of the reactants, and surface area. These all the things are affecting the reaction rate. Now let us discuss all the factors one by one. The first one is chemical nature of the reactant. All molecules do not react with each other. reactivity also depends upon the chemical nature of the reactant. Example, sodium instantly reacts with water, but iron reacts very slowly to produce rust. Copper reacts instantaneously with nitric acid at even room temperature, but does not react with water. So this is the nature of the reactant, how they will react. Concentration of reactants. You all know about it. If the concentrations of the reactants are high, the reaction is also fast. So higher concentration, faster reaction. Why? Because the particles are more likely to collide. Just see here, see this figure. This is the concentrations are low. The molecules are low. So low concentration, few collisions. And here the concentrations are more, high concentration, more collisions. Surface area of reactants. This I have discussed in the first lecture. Again here I am just saying higher surface area is equal to greater rate of reaction. You have all seen that. I have given you the example also. Particles are more likely to collide if the surface area is more. Now see here, hydrogen ions, see this figure, hydrogen ion can heat the outer layer of atoms only, just see that, the red one. But not these in the center of the lump. This. Okay. But come here in this one with the same number of atoms now split into smaller bits. There are hardly any magnesium atom inaccessible to the hydrogen ion. Am I clear to you? Because we are increasing the surface area. Clear to you? Effect of surface area on reaction. See that this is low surface area. Okay. So I'm just reacting CaCO3 plus 2HCl. It is giving you CO2 plus CaCl2 plus H2O. Now this is of higher surface area. I'm just dividing it into parts. So what it is that the reaction will take place more vigorously and we are getting the CO2 formation. Okay, we can see the CO2 formation, the higher rate. And see here the CO2 formation is in the slow rate. Presence of catalyst. Now catalyst is playing a very important role in a reaction. Now catalyst, as you know that catalyst is a substance that speed up the reaction without being a reactant or being used up. It is not taking part in the chemical reaction. Now see this graph. Here it is showing that the reaction, this is the graph for uncatalyzed reaction. This is the energy barrier. That means it is taking such a long time and the energy is also so high. From here to here, it has to cross this energy barrier for getting the product. But if we'll give the catalyst, now this one, this red graph is for the catalyzed reaction. That means catalyst is used. So it is decreasing the energy also. That means the reactant molecules, they have to cross only this amount of the energy, this much amount of the energy. This is the amount energy barrier here. And it is just, that means what? It is taking a very small amount of time also for forming the product. Okay, so what is that? Suppose this is a catalyst. See the catalyst. Now catalyst bonding to the reactants. Now in these two places, the reactants are just entering. Now release of the product and moving on for another reaction. Now after the reaction, whatever happening here, then it is just forming the product. See that two are colliding each other, giving you the product, and the catalyst is coming out as it is, and it is going for another reaction. It is moving for another reaction. Effect of temperature on reaction rate. According to collision theory, only those collisions affecting reactants acquiring energy equal to or above the threshold energy are effective and lead to products. That already I told you. According to collision theory, all collisions are not giving you product. Only those collisions will give you product which cross a certain energy barrier. That is a threshold energy. So if we'll increase the temperature, what will happen? Increase in temperature results into the increase in kinetic energy of the reactant, which in turn increase the energy due to collision. I told you this thing already. I explained this to you. If we'll increase the energy at temperature, the kinetic energy of the reactant will also increase. And if the kinetic energy of the reactant will increase, it can move faster. So naturally more collisions will take place, and those collisions may cross the energy barrier, that is a threshold energy. So more amount of collisions will take place in that way, effective collisions. Okay, so more product will form. Thus, one can expect that on increasing the temperature, number of collisions acquiring energy above or equal to threshold energy increases, as I told you. If we'll increase the temperature, number of collisions acquiring energy which may equal to the threshold energy or above the threshold energy. So naturally more product will form. This increases the rate of reaction. See this graph. We have taken three different temperatures, T1, T2 and T3. Now T3 is at higher temperature, then T2, then T1. Now just see at the temperature T1, which is the lowest temperature. In that temperature only this much amount, that means this D2A, only this much amount of molecules, they collide with effective, these are the effective collisions. That means very less amount of the product will form. Okay. Now increase the temperature, that is go to the temperature T2, see in temperature T2, the effective collisions are DE to A, this one, E to A. That means this much amount of product will form. Okay, so that means the product forming is much higher than the first one. Okay, now see in temperature T3. Now the effective collisions are from G to A, this one. So that means more amount of effective collisions are taking place, so more product will form. So as you are increasing the temperature, the kinetic energy of the reactant will increase, so their collisions will increase. Not only collision, the effective collision will increase. Okay, and more product will form. Activation energy, a very important term. For any reaction to take place, there is an energy barrier that the reactants must overcome. And this energy barrier is called threshold energy. This you all know. Now, activation energy may be defined as the excess energy that the reactant molecules must acquire through collision in order to cross the energy barrier or threshold energy. And then it will change into product. Okay, that means you all know that the reactant molecule, they possess certain amount of kinetic energy. Now, when they collide with each other, they have to cross a certain energy barrier to form the product. And you know it that all the collisions will not lead to the product. The collisions which cross the energy barrier, they will give you the product. So that means to cross that energy barrier, these reactant molecules must be activated. And this activation may be done by some external means, like increase in temperature. Okay, that means you can understand that the threshold energy, that is the energy barrier, is more than the kinetic energy that possessed by the reactant. And the difference between these two, that is the threshold energy and the energy of the reactant, come here and see that the activation energy is the threshold energy minus the energy of the reactants is known as activation energy. So this is the energy of the reactant and this is the threshold energy. The difference between these two, this one is known as activation energy. And you can see that the graph is starting from here and it is ending here. That means the energy of the reactant and the energy of the product, in between these two, energy of the product is much lower than the energy of the reactant. That means this is the difference between the energy of the reactant and the product, that is delta E. And delta E here is negative. Product minus reactant, energy of the product minus energy of the reactant. So energy of the reactant is high. So delta E is negative. And this energy will come out in the form of heat. Delta E is negative. That means the heat evolved. Negative value. So it is an exothermic reaction. You can explain exothermic and endothermic reaction from this graph by seeing the energy of the reactant and the product. If the energy of the product is high than the energy of the reactant, that means it is a positive delta E. That means it is an endothermic reaction. I think I am clear to you. Now, activated complex and transition state. A chemical reaction involves breaking of old bonds and formation of new bonds. That is known to you. A chemical reaction means it's a breaking of old bonds and formation of new bonds. Now, breaking of old bonds absorb energy and formation of new bond, it releases energy. That also you know. Now, suppose two molecules colliding with each other having necessary energy of activation through collision and approach each other and they attain an intermediate configuration before forming the product. Okay, it is an intermediate phase and after that, this will reach to the product. This intermediate configuration is called activated complex or transition state. This intermediate configuration corresponds to the maximum potential energy of the system. There is a maximum potential energy. This activated complex or the transition state, intermediate state. After that, that will lead to the product. Okay. Now, once the activated complex changes into product, it releases energy. So naturally, the intermediate state, that is the activated complex or the transition state, this is having the maximum potential energy of the system. Activated complex or transition state is shown here with an example. Suppose there is a reaction going on with a reactant A and BC. First of all, B and C is having a bond. Now A is far away from BC, so the potential energy is very low. No change in the potential energy in this case. Now, as atom A approaches to BC, the nuclei of atom B and C of molecule BC are forced to pull apart. And this involves the absorption of energy because B and C, the bond will break. Okay. As it is happening with the absorption of energy, the potential energy of the system will start increasing. Okay. Now, the increase in potential energy will continue till an intermediate configuration, that is the activated complex state, will reach. And in that state, the energy associated with the activated complex is equal to the threshold energy. So in this point, in this state, the system is having maximum potential energy. Okay, and as soon as the system attains the maximum potential energy, that is equal to the threshold energy, the activated complex decomposes and it will give you the product. And when it will give you the product, again the energy is released. And that is given with the help of this graph. Just see that this is the reactant A plus BC. Now it is far away. A is far away from BC. Now when A attacked BC, this bond will break with the absorption of energy and the energy will start increasing like this. Now this stage will reach to this stage, that is the activated complex, like this. This is the maximum energy and this is your activation energy. The energy difference between the threshold energy, this is your threshold energy, this is your threshold energy, and this is the energy of the reactant up to this much. This is your threshold energy and this is your energy of the reactant. So the difference between these two is your activation energy. When the reactant molecules reached into this state, activated complex state, then it is the maximum potential energy. It reached, it crossed, and then again it will start forming the product. And the product is forming here. Now it is forming AB and C is coming out. So in this stage, it is releasing energy. Now you can see that the energy here energy of the product is less than the energy of the reactant. The energy of the product is less than the energy of the reactant. So this is known as the difference in the energy, that is delta E. And as the energy of the product is less than the energy of the reactant, it is in the lower side. So it will give you minus delta E value. Minus delta E value for this case. In this case, it will give you minus delta E value. Now minus delta E means it will come out in the form of heat, and as it is a minus value, so that means this reaction is an exothermic reaction. See here, activation energy of activation is equal to energy of activated complex minus energy of the reactant. In another way, you can say that threshold energy minus energy of the reactant, because the activated complex, the energy of the activated complex is equal to the threshold energy. And delta E is equals to energy of the product minus energy of the reactant. This is known as activated complex. This is one example of activated complex. You are familiar with this example. This is a SN2 reaction of bromoethane with hydroxide. This you have read in standard 11 SN2 reaction. See that the bromoethane with that bromoethane hydroxyl ion is attacking from the rear side, from the back side. So it is forming a structure like this. This is known as activated complex. And then after formation of the activated complex, it is giving you the product. Beer is coming out and it is forming a product. That is ethanol plus and bromide are the product. Formation of ethanol, bromide ion. This is the example of an activated complex. Arrhenius equation. Arrhenius proposed a relationship between the rate constant and the temperature of the system. Only you have to know the formula. K is equals to AE to the power minus EA by RT, where A is the constant known as frequency factor, EA is the energy of activation, R is the gas constant, T is the temperature. And now taking logarithm on both sides, log EK is equals to log A, log EA minus EA by RT, or log 10K is equals to minus EA by 2.303 RT plus log 10A. Calculation of energy of activation through graphical method. Arrhenius equation in its logarithmic form, we have seen it in the last slide also, that log 10K is equal to minus EA by 2.303 RT plus log 10A. This is an equation of Y is equals to mx plus c. So it's a straight line graph. So if you plot a graph with log 10K and 1 by T, you should get a straight line, and the slope of the line will give you minus EA by 2.303 R. Okay. Now the energy of activation EA you can find from this graph, from the slope. Calculation of energy of activation by rate constant method. If K1 and K2 are rate constant of at two temperatures T1 and T2, then according to Arrhenius equation, you can write here log 10 K1 is equals to minus EA by 2.303 RT1 log 10 A. That means what is our equation actually? Log 10 K is equals to minus EA by 2.303 RT plus log 10A. Okay, now from here for the value of K1 and T1 I am getting this one, equation 1, with K2 and T2, I am getting equation 2. Now subtracting 1 from 2, we are getting this equation log 10 K2 minus log 10 K1 is equals to EA by 2.303 1 by T1 minus 1 by T2. Okay, minus sign not written here, so 1 by T1 minus 1 by T2, or log 10 K2 by K1 is equals to EA by 2.303 1 by 2.303 R 1 by T1 minus 1 by T2. Thus, knowing the rate constant K1 K2 at 2 temperature T1 and T2, you can find out EA from equation 3, energy of activation. Am I clear to you? Now, this is the end of lecture 4. In the next lecture, we will do molecularity of a reaction and we will solve some numerical based on Arrhenius equation.